Our planet has a story to tell. It's a story of fire and ice, of continents drifting and mountains rising, of life flourishing and, well, sometimes struggling to survive. This story isn't written in books, but in the very fabric of the Earth itself. It's etched into ancient ice, hidden in the mud of the deep ocean floor and recorded in the growth rings of the oldest trees. To understand our present and to wisely navigate our future, we really must first learn to read this planetary diary. The most crucial chapter in this story is the history of its temperature, a fluctuating rhythm that has dictated the course of life for billions of years. So how do we, in our fleeting moment of existence, come to know the climate of a world that existed long before us? The question of Earth's past climate is, honestly, one of the most profound inquiries of modern science. It's a detective story on a global scale. We can't simply travel back in time to place a thermometer outside a dinosaur's nest. Instead, we have to search for clues or proxies that nature has left behind. These are natural archives that have faithfully recorded the environmental conditions of their time. By piecing together these different clues from across the globe, a remarkable picture emerges. It's a picture of a planet that is dynamic and ever-changing, a world that has experienced climates far warmer and far colder than our own. This understanding isn't based on guesswork, it's built upon decades of meticulous scientific investigation. Our journey into the past begins with the tools we have today. We have satellites that orbit our world, constantly monitoring its vital signs. They measure the temperature of the oceans, the extent of the ice caps, and the composition of the very air we breathe. On the ground, a global network of weather stations provides a continuous stream of data, a legacy that stretches back for over a century. These direct measurements give us an incredibly detailed, high-resolution view of our planet's recent climate. But this detailed record, as valuable as it is, represents just a single tick of the geological clock. To truly grasp the scale of change, we need to look much, much deeper into the past. Understanding this long history isn't merely an academic exercise, it's a matter of survival. The climate we've enjoyed, the stable conditions that allowed human civilization to blossom, is a product of this long, complex history. By studying the great climate shifts of the past, we can understand the forces that drive them. We can see how life has responded to change, sometimes adapting, other times perishing. This knowledge provides the essential context for the changes we're witnessing today. It allows us to distinguish the natural rhythms of the planet from the new, powerful rhythm that's been introduced by humanity. Our future depends on our ability to listen to the Earth's story. Our most direct and familiar way of measuring temperature is, of course, with a thermometer. Since the mid-19th century, scientists and weather watchers have been systematically recording temperatures around the world. This instrumental record provides a solid foundation for our understanding of modern climate change. It shows with undeniable clarity a steady upward trend in global average temperatures, particularly over the last several decades. These aren't isolated readings from a single place, but a vast collection of data from land and sea, meticulously checked and cross-referenced. This network of thermometers has created a detailed, continuous narrative of our planet's warming over the last 150 years, a period of immense industrial and social transformation for our species. To venture further back beyond the reach of thermometers, we have to turn to one of nature's most magnificent archives, ice. In the polar regions of Greenland and Antarctica, snow has been falling and accumulating for hundreds of thousands of years. Each year's snowfall buries and compresses the layers beneath it, eventually forming a thick sheet of ice. This ice contains a remarkable record. Trapped within it are tiny bubbles of ancient atmosphere, perfect little samples of the air from millennia past. By drilling deep into these ice sheets and extracting long cylinders of ice, known as ice cores, scientists can travel back in time. These cores are like frozen time capsules offering a year-by-year account of the Earth's climate. The science of ice cores is wonderfully elegant. By analyzing the air trapped in those tiny bubbles, scientists can directly measure the concentration of greenhouse gases like carbon dioxide and methane from as far back as 800,000 years ago. But how do they determine the temperature? They do this by studying the water molecules that make up the ice itself. Water comes in different forms, or isotopes. The ratio of these heavier and lighter isotopes in the ice is directly related to the temperature at the time the snow fell. Colder conditions mean a lower proportion of the heavier isotopes. This method provides a reliable and astonishingly detailed temperature timeline stretching across ice ages and warmer periods. What these ice cores reveal is a beautifully clear pattern. They show that for hundreds of thousands of years, temperature and carbon dioxide levels have marched in lockstep. When CO2 was high, the world was warmer. When CO2 was low, the world was colder. This natural relationship recorded in the ice provides a powerful baseline against which we can compare our present situation. The ice cores tell a story of natural cycles, of a planet breathing in and out over vast timescales. But they also hold a warning, for the levels of carbon dioxide we see in those ancient air bubbles never ever reach the levels we have in our atmosphere today. The ice has given us a glimpse of the past and a yardstick for the present. While ice cores tell us the story of the poles, another remarkable archive lies waiting in the silent, dark depths of the world's oceans. Here, in the sediment that slowly accumulates on the seabed, are the remains of countless tiny creatures. Among the most important of these are foraminifera, or forams for short. These are single-celled organisms, protists that build beautiful, intricate shells or tests typically made of calcium carbonate. For millions upon millions of years, as these creatures have lived and died, their tiny shells have rained down upon the ocean floor, creating a layered library of climate history that stretches back far beyond what the ice can tell us, into a past of dinosaurs and ancient continents. The shells of foraminifera are a treasure trove of chemical clues. Like the ice in glaciers, the composition of these shells reflects the condition of the water in which they grew. Scientists can analyze the same oxygen isotopes within the calcium carbonate of the shells. The ratio of heavy to light oxygen isotopes reveals the temperature of the water at the time the foram was alive. Furthermore, it also tells us about the total amount of ice present on the planet. Because the lighter isotope of water evaporates more easily from the ocean to form ice sheets, the ocean becomes relatively enriched with the heavier isotope during an ice age. This signature is then locked away in the foram shells. To access this incredible record, scientists use ships to drill long sediment cores from the ocean floor. These cores can be hundreds of meters long, representing a continuous sequence of time spanning tens of millions of years. Back in the laboratory, the sediment is carefully washed and sieved to isolate the fossil foraminifera. Researchers then painstakingly pick out individual species under a microscope. By analyzing the chemistry of their shells layer by layer, from the newest sediment at the top to the most ancient at the bottom, they can reconstruct a detailed timeline of past ocean temperatures and global ice volume, a history that is truly epic in its scope. The story told by the foraminifera is one of profound and sometimes dramatic change. It reveals a planet that was once much warmer than today, a hothouse world with no polar ice caps and high sea levels. It also chronicles the long, slow cooling trend over the last 50 million years that eventually led to the ice ages we are more familiar with. By combining the data from foraminifera with evidence from ice cores and other proxies, scientists can build a comprehensive and robust history of Earth's climate. These tiny, long-dead organisms whispering from the abyss provide an essential long-term perspective, showing us that our planet is capable of climate states far different from the one we currently inhabit. The Earth's temperature has never been static. Over geological timescales, measured in millions of years, our planet's climate has undergone immense transformations, driven by powerful natural forces. One of the most significant of these is plate tectonics. The slow, relentless drift of continents across the globe fundamentally reshapes the planet's geography. This movement alters ocean currents, which are the great conveyor belts of heat around the world. The opening and closing of seaways, like the Drake Passage between South America and Antarctica, can isolate entire continents, allowing ice sheets to form and grow. The collision of continents also thrusts up great mountain ranges like the Himalayas, which can alter atmospheric circulation patterns and influence regional and even global weather. Volcanic activity is another major player in the Earth's climate drama. Individual volcanic eruptions can have a short-term cooling effect. Large eruptions like that of Mount Pinatubo in 1991 inject vast amounts of sulfur dioxide into the stratosphere. This gas forms a haze of sulfate aerosols that reflect sunlight back into space, causing a temporary global dip in temperature that can last for a few years. However, over millions of years, sustained volcanic activity can have the opposite effect. Volcanoes release enormous quantities of carbon dioxide, a potent greenhouse gas. Periods of intense, prolonged volcanism in Earth's past have been linked to hothouse climates, where high CO2 levels led to a much warmer world. On rare occasions, Earth's climate has been violently disrupted by events from beyond our world. The impact of a large asteroid or comet can trigger catastrophic and abrupt climate change. The most famous example is the Chicxulub impact 66 million years ago, which led to the extinction of the dinosaurs. The initial impact would have sent a superheated plume of debris into the atmosphere, followed by a global winter. Dust and soot would have blocked out the sun for months or even years, causing temperatures to plummet and photosynthesis to cease. After the dust settled, vast amounts of carbon dioxide released from vaporized carbonate rocks would have led to a period of prolonged warming. Such events are a stark reminder of the planet's vulnerability to sudden shocks. Finally, life itself has been a powerful force for climate change. The evolution of photosynthetic organisms like cyanobacteria billions of years ago fundamentally altered the atmosphere. These tiny microbes began to pump vast quantities of oxygen into the air, while drawing down carbon dioxide, a process that cooled the planet and paved the way for the evolution of complex life. Later, the spread of land plants further reduced atmospheric CO2 and changed weathering patterns. These biological processes show that the climate is not just a stage on which life acts out its drama. Life is an active participant, capable of shaping the very conditions of its own existence. These great forces operate on timescales far beyond a human lifetime, yet they have sculpted the world we know. Within the grand sweep of geological time, there is a more regular, predictable rhythm to Earth's climate. This is the pulse of the ice ages. For the past 2.5 million years or so, our planet has been oscillating between long, cold, glacial periods, where vast ice sheets covered much of North America and Eurasia, and shorter, warmer interglacial periods, like the one we are in today. These cycles are not random, they are driven by subtle periodic changes in Earth's orbit around the Sun. These predictable variations are known as Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who first calculated their effects in the early 20th century. There are three main components to these orbital cycles. The first is eccentricity, which describes the shape of Earth's orbit. Over a period of about 100,000 years, the orbit changes from being nearly circular to more elliptical and back again. When the orbit is more elliptical, the Earth receives more solar radiation when it is closer to the Sun and less when it is farther away, amplifying the seasons. This 100,000-year cycle has been a dominant beat in the Ice Age rhythm for the past million years. It is a slow, gentle push that can nudge the climate system into or out of a glacial state. The second cycle is axial tilt, or obliquity. The angle of Earth's axis of rotation relative to its orbital plane is not constant. It rocks back and forth between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. A greater tilt means more extreme seasons, hotter summers and colder winters, especially at the poles. A smaller tilt leads to milder seasons. This is crucial because cool summers in the northern hemisphere are thought to be the key to starting an ice age. If summer snow doesn't completely melt, it can build up year after year, eventually forming a massive continent-spanning ice sheet. The final component is precession, or the wobble of Earth's axis, like a spinning top that is slowing down. This wobble operates on a cycle of about 26,000 years. It determines which hemisphere is tilted towards the Sun when the Earth is at its closest point in its orbit. These three cycles, eccentricity, tilt, and precession, interact with each other in complex ways. They don't change the total amount of solar energy the Earth receives over a year, but they do change its distribution, both geographically and seasonally. They act as the pacemaker of the ice ages, initiating periods of warming and cooling that have profoundly shaped the landscape and the evolution of life, including our own species. The Milankovitch cycles and other natural forces have governed Earth's climate for millions of years, producing gradual shifts over vast timescales. The transition from a deep ice age to a warm interglacial period, for example, typically involves a warming of about 4 to 7 degrees Celsius. However, this warming, as seen in the ice core records, is a process that unfolds over thousands of years. The planet takes its time to adjust. Ice sheets melt slowly, oceans warm gradually, and ecosystems have generations to adapt or migrate. This natural pace of change is the critical baseline against which we must measure the climate shifts we are experiencing today. It is the steady, long-term rhythm of the planet. What we are witnessing now is profoundly different. The warming that has occurred since the dawn of the Industrial Revolution, and particularly in the last 50 years, is happening at a speed that has no known precedent in the geological record. The global average temperature has risen by more than 1 degree Celsius in just over a century. While that may not sound like much, it represents an astonishingly rapid accumulation of energy in the Earth's system. The rate of this warming is roughly 10 times faster than the average rate of warming after an ice age. It is a sudden, sharp spike that stands out dramatically from the gentle rolling hills of natural climate variability. This speed is the crucial factor. Imagine a car gently rolling down a long, shallow hill over the course of an hour. That is natural climate change. Now imagine that same car accelerating to motorway speeds in just a few seconds. That is the change we are causing today. The Earth's systems, its oceans, its ice sheets, its forests, and its diverse species are adapted to the slower, more gradual pace of change. They're not built to withstand such a sudden and violent jolt. The speed of the current warming is overwhelming the capacity of many natural systems to adapt, pushing them into uncharted territory. The evidence for this unprecedented pace is overwhelming and comes from every corner of our planet. We see it in the rapid retreat of glaciers worldwide, from the Alps to the Andes. We see it in the accelerated melting of the Greenland and Antarctic ice sheets, which is now a major contributor to sea level rise. We see it in the warming of the oceans, which have absorbed the vast majority of the extra heat. We see it in shifts in the timing of seasons, with spring arriving earlier and autumn later. All these observations paint a consistent picture of a world changing at a breakneck speed, a speed that cannot be explained by the slow, stately dance of Milankovitch cycles or other natural drivers. If the current warming is not caused by the natural cycles that have governed Earth's past, then what is its cause? The answer, established by an enormous body of scientific evidence, is unequivocal. It is us. The rapid change began around the time of the Industrial Revolution in the 18th and 19th centuries, when humanity began to burn fossil fuels, coal, oil and natural gas, on a massive scale to power our factories, our homes and our transport. The burning of these fuels releases huge quantities of carbon dioxide, or CO2, into the atmosphere. This CO2, which had been locked away underground for millions of years, is a powerful greenhouse gas. The greenhouse effect is a natural and essential process. Gases like carbon dioxide, methane and water vapor in our atmosphere act like a blanket, trapping some of the sun's heat and keeping our planet warm enough for life to thrive. Without this natural greenhouse effect, the Earth would be a frozen, uninhabitable world. The problem is not the existence of the effect, but the fact that we are thickening that blanket. By adding vast amounts of extra CO2 and other greenhouse gases, we are trapping more and more heat, causing the planet's average temperature to rise. This is the fundamental mechanism of modern climate change. The evidence linking human activities to rising CO2 levels is irrefutable. We know how much fossil fuel we burn each year, and therefore we know how much CO2 we are releasing. The concentration of CO2 in the atmosphere, as measured at observatories like Mauna Loa in Hawaii, has risen from around 280 parts per million before the Industrial Revolution to over 420 parts per million today, a level not seen in at least 800,000 years, according to the ice core records. Furthermore, chemical analysis of the carbon in the atmosphere shows that its isotopic signature matches that of carbon from fossil fuels, providing a clear fingerprint of the source. This human-caused warming is not just a theory. It is a documented fact, confirmed by multiple lines of evidence. Climate models, which are sophisticated computer simulations of the Earth's climate system, can only reproduce the observed warming of the past century when they include the effects of human greenhouse gas emissions. When the models are run with only natural factors like solar activity and volcanoes, they fail to match the reality of the warming we have experienced. The conclusion is inescapable. The dramatic and rapid warming of our planet is the direct consequence of our own actions. We have become a geological force in our own right. The rapid pace of climate change poses a profound threat precisely because it disrupts the delicate balance to which life on Earth, including our own human societies, has adapted. Ecosystems are intricate webs of relationships that have evolved over millennia under relatively stable climate conditions. When the climate changes too quickly, these webs begin to unravel. Species may try to migrate to cooler areas, but they may be blocked by mountains, cities, or oceans. Their food sources or pollinators may not be able to move with them. The result is a growing risk of extinction. We see this happening already with coral reefs, which are bleaching and dying in warmer, more acidic oceans. The consequences for humanity are equally severe and far-reaching. Rising sea levels driven by the melting of glaciers and the thermal expansion of seawater threaten coastal communities and cities around the world, where hundreds of millions of people live. The warming atmosphere holds more moisture, leading to more extreme rainfall events and devastating floods in some regions. In other areas, the same warming leads to longer and more intense droughts and heat waves, threatening water supplies, agriculture, and human health. The very stability of our food systems is at risk as traditional farming practices become unviable in a changing climate. Furthermore, a warmer world is one of more extreme weather. Hurricanes and typhoons draw their energy from warm ocean waters, and there is evidence that they are becoming more intense, with stronger winds and heavier rainfall. Wildfires are becoming more frequent and widespread as forests dry out during prolonged droughts. These extreme events not only cause immediate destruction and loss of life, but also have long-term economic and social consequences, displacing populations and putting immense strain on infrastructure and emergency services. The costs of inaction are mounting with every passing year, measured in lives lost, homes destroyed, and economies disrupted. The threat is not just physical, it is a threat to the stability and prosperity of human civilization. Climate change acts as a threat multiplier, exacerbating existing problems like poverty, inequality, and political instability. Competition over scarce resources, such as water and fertile land, can lead to conflict. Mass migration driven by climate impacts constrains social and political systems. The intricate global economy, which relies on predictable supply chains and stable conditions, is vulnerable to the disruptions caused by a chaotic climate. In short, the rapid change we have unleashed is putting the very foundations of our modern world under immense and growing pressure. Our planet has been hotter in the distant past than it is today. During the age of the dinosaurs, for example, CO2 levels were much higher, and there were no polar ice caps. The Earth survived, life survived, but it is crucial to understand that the planet's survival is not the same as our own. The real danger of modern climate change is not that the Earth will be destroyed, but that the rapid rate of change will make it a much more difficult and dangerous world for human civilization to inhabit. The key takeaway from Earth's long climate history is that the speed of change matters more than the absolute temperature. It is this unprecedented speed that we must now address. The global scientific community, through bodies like the Intergovernmental Panel on Climate Change, or IPCC, has laid out a clear path forward based on our understanding of the climate system. The foremost and most urgent task is to dramatically reduce our emissions of greenhouse gases. This means transitioning our global energy system away from fossil fuels and towards clean, renewable sources like solar, wind, and geothermal power. It requires improving energy efficiency in our buildings, industries, and transport. The goal is to reach net zero emissions, a point where any remaining emissions are balanced by their removal from the atmosphere as quickly as possible. Alongside reducing emissions, we must also explore and develop methods for removing existing carbon dioxide from the atmosphere. This is known as carbon dioxide removal or carbon capture. Some of these methods are natural, such as reforestation and improving soil health to absorb more carbon. Others are technological, involving machines that can directly capture CO2 from the air and store it underground. While these technologies are still developing and cannot replace the need for emission cuts, they will likely be a necessary part of the solution to stabilize our climate. This two-pronged approach, radical emissions reduction and active carbon removal, is our best hope. Ultimately, understanding our planet's past is the key to making wise decisions about its future. The ice cores, the ocean sediments, and the geological record have given us a profound gift. The knowledge of how our planet works. They show us the natural rhythms and the powerful forces that have shaped our world. They also provide a stark warning by showing us just how unusual and dangerous our current trajectory is. The story of Earth's climate is a story of cause and effect. We are now the primary cause of change, and we have a choice about the effect we want to have. Heeding the lessons written in the rock and ice is not just a scientific imperative, it is our responsibility to future generations.